Mm. Hello. So I'm just going to clear up a few things, um, just about physicals, quantum field theory, observer relativity in particular, and devised a theory that accounts for quantum mechanics and special relativity in its entirety, believe it or not. And that dilation, if you think about dilation, right, it's normally thought of relative to that of a body in the surface of the Earth. If you have Einstein's tram and you're traveling on Einstein's tram, because you're traveling in a horizontal fashion, objects, if you were traveling very quickly, and the dilation relative to your position, they would become elongated, like people would become tall and they would be compressed and become short in this kind of manner. And then if you were to walk around the Earth in any direction, if you are to fly a plane, go on a train, go on any kind of transport, the same kind of ideology of dilation will exist, right? Now, the Earth moves in a corkscrew rotation, right? But don't worry about that too much. What you're familiar with is your perspective from on Earth. Now, from that perspective, if you were to travel in a corkscrew spin fashion, right? You were on a tram and somehow it traveled in a corkscrew spin with a contour integral or that of a increasing gradient in velocity. Now, what would happen is if you were looking at a square building per se, that one corner of the square building would become compressed and the opposite corner would become more elongated, and dilation would resemble that of broken symmetry, right? As you increase in velocity, the symmetry will become increasingly broken until eventually it becomes fully dilated and it will appear as a drastically elongated one-dimensional line. And this one dimension, that is where there will be two squares. In reality, you won't be able to see them, but in reality, there'll be two squares. There'll be a pheromone square and there'll be an anti-square. And that is how dilation works. Okay? And that is how it's relative to quantum mechanics and that of classical mechanics. That's how it works. Now, if I have this geometry here that I'm working on, and it's time parity. It's time parity broken symmetry, which constitutes SUSY or supersymmetry, which is what I've been working on for a while. That's still very much something that works. But, it's derived from this, as I previously stated. It's a set of Pythagorean triangles, and then they're rotated in a corkscrew spin. And then this part here is the most dilated part, right? It's the most dilated part. In reality, it would be a lot longer. And then come back over here. The dilated part is relative to an undilated part. And then I'm using tetrahedrons to show dilation relative to undilated parts. And it comes in the form of different tetrahedrons. So these vertices of one tetrahedron will correspond to a dilated vertice of a opposing or relative to a different tetrahedron. and I have to put all the bases in still, and there's a bit of work to be done, and like I'm going to have to change the geometry of this and adjust it accordingly for it to actually be mathematically precise. It's going to take quite some time. And yeah, this is what supersymmetry is. Supersymmetry is actually about time parity dilation. And yeah, the observer relativity, like it's an illusion because you're on the Earth always spinning in a corkscrew rotation. The classical descriptions of special relativity are true and correct, but need to be elaborated on in this very fashion. And then if you want to talk about quantum entanglement, superposition, okay, let's talk about that. Well, you have annihilation and that of fusion and or annihilation in the sun, for example, or in quasars. And when you get entangled, that's how you get entangled photons. And then entangled photons correspond to the absorption, reflection, refraction of that of other particles, right? And nothing travels faster than the speed of light. So this spooky action at a distance, which is quite a silly name to be honest, that's why there appears to be a transmission of information that's faster than the speed of light. But the origin of entanglement of photons derives from the annihilation, and it stores and holds this information, this signal, and it doesn't travel faster than the speed of light. The information is stored in the entanglement initially, and that is obvious, and it is ludicrous not to think so. Okay. And then the problem is when you get two very precise telescopes and you point them at two quasars and you want to measure how photons are entangled, how entanglement works. Well, there's variabilities in your measurements because quasars shoot photons in opposite directions. And that means that, say, if you put a complex value on one direction and a whole value on the other direction, then you don't know, there's variabilities or there's an amplitude of different types or qualities of entanglement, and therefore it's an inaccurate, unviable methodology of defining entanglement. So that poses a very real problem. And yeah, I could go on and on, but I also have this geometry. I did this. This is just like, it's a piece of art, I guess. Like it's a lot fancier than it needs to be. But yeah, it's pretty cool. It's very small. Look, that's my finger. That's a 30 centimeter ruler. And this picture is a derivative of this vector. So this is a vector. It's a vector of Pythagorean triangles that are rotated in a corkscrew contour integral. And the contour integral is that of angles of the surface. And this is an inversely proportional version of this. And this section here and this section here are combined to form a derivative. So this is the inverse section, these ones. These are the outer sections, and they're all entwined and whatnot. So it has like some representations like of internal properties of reality, but not really. It's more of a expressionist piece of art. Yeah, that's what I've been up to. I feel as though people don't really understand time parity dilation and that of even entanglement. And I just wanted to clear these things up because it's pretty important. So yeah.